Dear students, let us continue our study on organic spectroscopy, and in this module also we shall discuss about some combined problems based on UV, IR, 1H NMR, 13C NMR and mass spectroscopy. After studying this module, you shall be able to learn how to derive the structure based on the information given in these different spectra. They can be UV spectra, 1H NMR spectra, 13C spectra, IR spectra and mass spectra. And some questions there will be one or two spectra, or in others there will be combination. So, we will see how, based on what information you are given, we can come to the conclusion, and if you are given some values and not the spectra, get the information regarding the structure of the compound. But before we get started on solving problems, while analyzing the data, you should be always keeping these things in mind, which I have told you earlier, but I will repeat. That is, in the UV visible spectroscopy, we get the information about the conjugation, the carbonyl type of groups. The IR spectra or the IR values, if they are provided you, they will give you information regarding what functional group is present, and you can always refer to the literature value for that this particular group comes at this value. So, it will correspond to this particular functional group. The 1H NMR will give you information and environment of neighboring hydrogen atoms which are present. The 13C NMR will tell you the information about the different type of carbon atoms which are present in the molecule, and the mass spectral data will give you information about the total mass and fragmentation pattern of that molecule. And by combining all this information, one can very easily find the structure of the given unknown organic compound. So, let us begin with this question. A volatile compound with molecular mass 130 contains 73.85% carbon and 13.5% hydrogen. The compound is transparent above 210 mu in UV region. In its IR region, bands are formed at 2960 to 2851 as multiplied. Then there is a 1342 band and 1075 centimeter inverse, which is at singlet. Only a singlet at 8.95 tau is formed in its NMR spectra, and you have to derive or find the structural formula based on this information. Let us see how to solve this question. As provided to us, carbon is 73.85%, hydrogen is 13.50%, but this is not totaling to 100. So, obviously, there is oxygen which is 12.3%. And based on this information, we can calculate the empirical formula that you know how you can do. We get that it is the C8H18O. Since the compound is transparent above 210 mu in the UV region, it shows the absence of carbonyl group, nitrogen containing group and conjugation, etc. So, this is the important information we can derive from the UV data. In the IR region spectra, there is most characteristic 1075 centimeter inverse for an ether, that is CO stretching, and there is the COC group. The other bands at 2960 to 2851 and at 1342 centimeter inverse are for CH stretching and CH bending vibrations respectively. The appearance of only one singlet at the high field 8.95 tau reveals that all the alkyl groups in the compound are in exactly similar environment, and it is only possible if the structure of the compound is as shown here, because then all these 9 plus 9 hydrogens you can see in these 6 methyl groups attached to these carbons through this ether bond. So, this will be the only possible structure, and this will explain all the data which is provided to you in this question. So, the compound here is this di-tertiary butyl ether. Let us move to next question. The carbonyl stretching absorptions for the given lactones, as you can see here, they are 1745, 1720 and 1760 centimeter inverse. So, you are provided these 3 lactones and you are given these 3 values. You have to match the absorptions with the appropriate structure and give a reason for each choice. Let us see how to do this matching. The carbonyl stretching absorptions for the lactones, as you are provided, for first it will match with 1745, for the second structure will match with 1720, and for the third it will match with 1760 centimeter inverse. And why it is so? Let us try to understand. In the lactone 3, the conjugation of CC double bond with carbonyl group will result in an increase in the double bond character of the carbonyl group, and consequently an increase in the carbonyl frequency will occur as compared to the saturated lactone, which is 1. So, that is why the saturated lactone 1 is having value 1745, but the 3 will have a higher value of 1760 inverse, and obviously the second one, which is not conjugated, it will be coming at the lesser value at 1720. Let us move to another question. How will you distinguish between cis and trans stilbenes on the basis of PMR spectroscopy or the 1H NMR spectroscopy? To get the answer for this, let us write the structure of cis and trans stilbenes, and they are as you can see here. Cis and trans stilbenes can be distinguished from their respective chemical shift values. In trans stilbene, a planar structure, each for the 2 olefinic protons labeled as HA, is de-shielded by both aromatic rings. On the other hand, in cis stilbene, each hydrogen HB is de-shielded by only one adjacent aromatic ring. HAs therefore appear at low field than HBs, that is HAs will appear at 7 delta and HBs will appear at 6.05 delta ppm respectively, and that is the basis how you can make the differentiation between the cis and the trans stilbene from their PMR spectra. Let us move to another question, which is, why aren't all proton magnetic resonance signals found at the same frequency? After all, they all arise from the magnetic properties of the same nucleus, that is hydrogen. And how this question can be answered? The resonance condition delta E is equal to h mu is satisfied when delta E is equal to F gamma B, where B is the value of the magnetic field at the hydrogen nucleus being observed. B can be regarded as having 3 components: B0, the external applied magnetic field; B1, the field due to electrons circulating near nucleus being observed, and this is called as the chemical shift delta; and there is B2, which is the local magnetic field due to other magnetic nuclei, that is other than hydrogen nuclei, near the observed hydrogen nucleus, and this is called J or spin-spin coupling. So, in general, differently situated hydrogen nuclei, they resonate at different mu values. Let us move to the next question. How many different chemical shifts do you expect for hydrogen nuclei in these particular molecules that you can see here? And where there is more than one chemical shift which will be expected, and what will be the relative intensities of the different signals in these written 4 molecules? Let us see how to answer this. In CH4, all the hydrogen nuclei are equivalent since the molecule has a regular tetrahedral shape. Equivalent protons have the same chemical shift and do not give rise to J splitting. Only one chemical shift is expected. In case of CH3, the argument is the same as for methane and only one shift is expected. A useful test for magnetic and chemical equivalence is to replace mentally the hydrogens in the question by a chlorine atom. If you get the same compound, then the nuclei are equivalent. Thus, ClCH2CH3 is the same compound as CH3CH2Cl. But in case of propane, that is CH3CH2CH3, the two terminal methyl groups are magnetically as well as chemically equivalent, and so their hydrogen atoms will have all the same chemical shift. The central CH2 group is different and will have a resonance signal at a different chemical shift. So, two different chemical shifts are expected. Their relative intensity, if we talk about, will be having the same ratio as the number of hydrogen nuclei in different environment, that is 6:2 or we can say 3:1. Coming to ethene, that is CH2CH2, here all the hydrogen nuclei in this planar molecule are equivalent, and you can again try the chlorine substitution test here also. Only one chemical shift will be obviously expected. In case of CH2CHBr, that is vinyl bromide, each hydrogen nucleus in this planar molecule is different. This you can come to know by doing the chlorine replacement test, and you will get three different molecules. So, there will be three chemical shift that will be expected with intensities in the ratio of 1:1:1:3. So, here in the case of vinyl bromide, there will be three chemical shifts which will be expected with intensities in the ratio of 1:1:1. Let us take another question here. What spin-spin coupling patterns will you expect for each distinct set of hydrogen nuclei in these given molecules? They are CH3CHCl2, CH3CHClCH3 and this methyl ethyl ether. Now, let us see how to get this answer. In case of CH3CHCl2, there are two different chemical shifts for the hydrogen nuclei in this compound. The n+1 rule will tell us that for the methyl group, the single hydrogen nucleus in the adjacent CHCl2 group will split its signal into 1:1 doublet, that is 2 equal peaks. For the CHCl2 group, the 3 protons in the adjacent methyl groups will split its signal into a quartet. So, 4 peaks of relative intensities 1:3:3:1 will be there. The total intensities of the two signal, if we talk about, will be in the ratio of 3:1. Coming to the next molecule, in case of 2-chloropropane, for the CHCl group, the 6 equivalent hydrogen nuclei in the 2 adjacent and equivalent methyl groups, as you can see here, will give rise to 7 peak signal, which will be a septet. For the 2 equivalent methyl groups, the single hydrogen nucleus in the CHCl group will be responsible for a doublet signal. Talking about the total intensities of the two signal, it will be in the ratio of 1:6. In this next molecule, which is methyl ethyl ether, the ether oxygen with its bonds mean the magnetic effects of the sets of hydrogen nuclei on the two sides of the ether O are not transmitted through. Thus, the 3 hydrogen nuclei in the CH3O group will give rise to one unsplit signal. And for the OCH2CH3, we will expect a quartet for the methylene group and a triplet in the ratio 1:2:1 for the methyl group. If we talk about the total intensities for the 3 signals, they will be in the ratio of 3:2:3, which is corresponding to the number of hydrogens in them.